algebraic geometry, which is a new area at the interface between algebraic geometry and combinatorics. So assuming that, not knowing your backgrounds and assuming that at least the combinatorics is new to many of you, the plan is to take it fairly slowly for the first few days. So a rough outline is, for the first 3 days, we're going to sort of do the sort of introduce tropical varieties, and then the last 2 days, hopefully we'll say a little bit about connections with some more sophisticated algebraic geometry. But the plan is that the first few days should be fairly elementary. Please do ask, well, for the whole week, please do ask questions if anything's unclear. I have some notes. At the moment, it's only the first lecture here. This is linked from my webpage, so the easiest way to find this is to Google me. I'm the only Diane Maclagan who shows up on the first page, and then go to, this is posted on under lecture notes of my papers. I'm also writing a book with Bert Sturmfeld. There's a draft available also here, and we would very much welcome any comments on those.
So we will leave a copy at the photocopy machine if you want to copy this lecture notes.
Okay, so what is tropical geometry? Tropical geometry is algebraic geometry over the tropical semiring. Okay, this is where we replace multiplication by addition and addition by minimum. So let's start by, well, maybe I should, so tropical geometry, so it's algebraic geometry over the tropical semiring. Okay, so what is that? That is, so this is, so the tropical semiring that's going to be R union infinity. We have two operations. We have tropical plus, A plus B is the minimum of A and B, and A times B is the usual A plus B. Okay, so we can see this is these are distributive, they're associative. We have here the additive identity. Is infinity. The minimum of 7 at infinity is 7. And the multiplicative identity is 0. Okay, so anything tropical times 0, that's anything plus 0, so it's just the number you start with. Okay, so you can see that this is associative, distributive, these are identities. We have almost everything we need for a ring, except there's no subtraction. Just say no subtraction. However, things are still nice, so this is why it's a semi-ring. I should say a semi-ring is just something that satisfies all the axioms of a ring, except the subtraction. And this was studied a long time, for at least many decades before algebraic geometers got into the game, primarily starting from semi-group theory, optimization, and so on. The name tropical semi-ring, for any Brazilians in the room, comes from, this is in honor of, I guess was named by a French computer scientist in honor of the Brazilian computer scientist Emre Simão. So the tropical here refers to Brazil. Okay, so what do we know about all of this? Well, as I said, it's still nice. For example, we have what in North America is called the freshman's dream. Okay, if I try and multiply out x to the n, x plus y to the n, you'll see that this is, well, this should be a plus, tropical plus. This is x to the n plus y to the n. Okay, let's check that. So to the n means times, 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 n times. So I've got the minimum of x plus y, plus the minimum of x plus y, plus the minimum of x plus y. So that's just n times the minimum of x plus y. Okay, which is what this is. And that's clearly the same as n times the minimum of n times x and n times y. Okay. And this example, in some sense, is what tropical geometry is all about. Everything is just a little bit easier. Okay? So the goal of what we want to do is to say, okay, things are easier, can we still do what we wanted to do? So what we're going to do eventually is start with varieties, tropicalize them to get what we call tropical varieties, and the goal is going to be to recover the information we wanted to know about the variety from the tropical variety. And you have to remember this sort of example, things are easier in tropical geometry. Okay. So since we want to move towards doing algebraic geometry, we should talk about polynomials. So tropical polynomials are piecewise linear functions. Linear functions. So as an example, let's take a cubic equation. So if I take minus 2 times x cubed, tropical plus minus 1 times x squared, tropical plus 1 times x plus, I just switched to, yeah, okay. I switched to my multiplication symbol, so plus tropical times 5. Okay, so what is this? In usual arithmetic, the pluses become minimum, so this is the minimum of x cubed is x times x times x. The usual arithmetic, that's 3x. So we've got the minimum of 3x minus 2, 2x minus 1, x plus 1, and 5. So, as a function, polynomials are functions from the field to the field. Here we've got a function, I want you to think about it as coming from r union infinity to r union infinity. So as a function, we're going to have the minimum is the constant function up to x equals 4. It is then the function x plus 1 up to x equals 2. So here we have this is 5, this is 3. We then go down to the point 1, 1. That's the function 2x minus 1. And then we have the function 3x. So the point you should take away is we started with a polynomial and we get a piecewise linear function. Okay? Again, much simpler. In fact, we tried to teach people having trouble sketching polynomials. Here we're just drawing straight lines. I want to do another example because we want to think about polynomials in more than one variable. If I take x plus y plus 0. Okay. Now, of course, this is to remind you in usual arithmetic we never write plus 0. But of course, 0 is not the additive identity. So this has some content. In usual arithmetic, this is the function, the minimum of x, y, and 0. So what is this? This is a function from R2 or from R2 union infinity squared to R, or to R union infinity. Let me draw just the domain. Here it's going to be the function 0. Here it will be the function y, and here it will be the function x. So this is the positive x-axis, this is the positive y-axis, and this is the negative y equals x. Okay, so you can imagine, if you imagine the graph, it's going to be flat, and then go sort of down in these two directions. Okay, so this is another tropical polynomial, just the line, x plus y plus 0. Okay, so here, those are two examples of tropical polynomials. Okay? We want to talk about varieties, so that means we want to look at the common solution to some polynomial equations. Okay? We have an obvious problem though, which is with no subtraction, how can we solve equations? Okay, for example, if I want to look at the x tropical plus 2 equals 5. Okay, so let's pause for a moment. What is the solution to x tropical plus 2 equals 5? So normal arithmetic, right? I'm asking you for a number x where the minimum of x and 2 is 5, and of course you know that this doesn't exist. Okay, so this is a problem. Right? What's the solution? I'm going to tell you the solution now, but it won't make as much sense why this is the solution until tomorrow. So that's going to be, the solution is, instead of looking at equals 0, in some sense, for a start, it should be equals infinity. So again, this is, notes, Google to find my webpage. There are notes under lecture notes and a draft book on the draft book. Okay, so the solution is we're going to look at the graph of f, and we're going to consider where does this function trop f differentiable or linear. Okay, so the solution is that the hypersurface defined by the tropical polynomial f by the tropical polynomial f is the non-differentiability locus. So it is the non-differentiability locus. Okay, so this is the place I have a function. It's a function from r to the n to r, or from r union infinity to the n to r union infinity. I want to look at when it is differentiable. Or equivalently, it's the, so this is the non-linear locus of capital F. Or equivalently, it's going to be the set of w in r to the n such that the minimum in F is achieved at least twice. Okay, so you think about this. We have a function, it's a polynomial, so that means it has a form that looks like this. It's a minimum of a bunch of linear functions. When is the minimum of a collection of linear functions not differentiable, or when is it not linear? Exactly when the minimum is achieved at least twice. So in this picture, we have, here is a problem, here is a problem, and here is a problem. Okay, so that's going to be the tropical solutions to this cubic equation. Okay? And you'll notice in this case that we have exactly 3 solutions to my cubic equation. Again, the hypersurface is going to be the locus where the minimum is achieved at least twice. So this means, well, I guess maybe before if we look at the second example over here, here again, here was my polynomial in usual arithmetic. Here was the picture of the domain, and you can see that what I've really drawn is the non-linearity locus. Okay, so my tropical variety is precisely just these 3 line segments. So the positive x-axis, the positive y-axis, and the negative y equals x. Okay, so that's the region where the minimum, so this is y equals 0 is less than or equal to x. This is x equals y, so x equals 0 is less than or equal to y. And this is x equals y is less than or equal to 0. Okay, so the minimum is achieved at least twice. So you notice the quadratic formula is particularly simple here. So look. If we have f is going to be a times x squared, tropical plus b, tropical times x, tropical plus c. Okay? So if I draw, this is a function for various choices of a, b, and c. This is a function from r union infinity squared to r union infinity. Let's draw the graph. And of course, it depends on what a, b, and c are. So I might have, this is the line y equals c, this is the line y equals x plus b, and this is the line y equals 2x plus a. Okay, so first of all I tropicalize, with usual arithmetic. This is the minimum of 2x plus a, x plus b, and c. So I draw, this is a minimum, and I'll get here, this is the points c minus b, comma c, and this is the point b minus a, comma 2b minus a. Okay, so if this is the right picture to draw, then my roots or the solutions are going to be c minus b and b minus a. Of course, that assumed that my picture was correct. If you do the algebra, you see, what do I mean by my picture being correct? That means that this piece actually exists. Okay, if you draw it, you can see eventually for large x, y equals c is the smallest. For very small or large negative x, y equals 2x plus a is the smallest. But whether this piece actually shows up depends on the relative size of a and b. So what it depends on is whether 2b is less than or equal to a plus c. Okay, and otherwise, if we take this the whole way up, if I sketch here, this is the point c minus a over 2, comma c, and otherwise it's just c minus a over 2 if, do I have this right the right way? If 2b is at least a plus c. Okay. Now, of course, this will look familiar to you, right? In the context of a quadratic equation, we have seen 2b and a plus c before. Okay. Why? Well, what is 2b? This is the usual arithmetic way of saying the tropical b squared, and I'm saying a times c. Okay, so I'm comparing the size of b squared and a times c. Something has happened to the 4 in the discriminant, but maybe we'll come back to that tomorrow. Okay, so this is an example. Here we have, tropical arithmetic is easier. Here we have the quadratic formula. Okay, to make it more convincing that it's easier, you should work out the tropical cubic formula, the tropical quadratic formula. Okay, these are honestly easier. Speaking as someone who's never really learned the formula to solve a cubic. Okay, so maybe this is a good. So the goal, as I said, of the first part of the week is to just build up. The structure of tropical varieties. At this point, we could go in several different directions. Okay, I'm going to follow the idea of tropicalizing embedded varieties. We could continue in this fashion and build up all of algebraic geometry over the tropical semi-ring, as much as is possible. Okay, this is an approach that's taken particularly by Christian Maclagan and his school, is to just start, let's work purely in the tropical semi-ring. The other approach, though, is to try and make a tighter connection with classical algebraic geometry. And that's the approach we'll take this week, where we're going to talk about starting with varieties, not over the tropical semi-ring, and tropicalizing. Okay, so that's going to be the goal for the week. So maybe I should pause. Questions?
So there you start with the normal quadratic formula and tropicalize it, find the roots. Could you explain again what these roots tell us about the original?
Okay, so I might want to put that, so I'm going to ask you to ask that question again tomorrow. Okay? So it's a little unfair, right? So at the moment, I haven't really explained where it's coming. So at the moment, you could say we're playing a game. Okay? We're just doing, you could think about this as algebraic geometry as if we're working over the tropical semi-ring. So I've declared that this is the notion of root. Okay, maybe I should say, as a preview, what we're going to see is that this tells us something about the size of the roots. So we're going to see that if I worked over a field with valuation, these will be the valuations of the roots. Okay. But maybe let's come back to that point. Yeah, ask that question again tomorrow if it's not there. Yeah. So maybe more questions? Right, yeah, so that's another, we can at least, that's true, yeah, we can use the roots to factor it over the tropical semi-ring. Yeah, that's a good Though there, this is something where one has to be it's a little strange that things are much, somehow life is a lot easier over the tropical setting ring, partly because functions, you can have several different polynomials that give you the same tropical setting, that give you the same function. So if I'm in this situation where 2b is bigger, that means that it doesn't matter how much bigger I make b, I won't change the function. So that's one of the strangenesses of the tropical loop. Okay. So maybe what we want to do now is start to make this connection. So actually, maybe I'm not sure whether, maybe we can just get today to explain the quadratic formula. So what I want to do now is assume that I'm working over a field with evaluation. So this is the connection with classical algebraic. So algebraic geometry. Okay, so let's K be, so capital K is a field with evaluation. So I remind you, this is a function val from K star, which is, that's K take away 0, into the real numbers that satisfies the axioms. The valuation of A times B is the valuation of A plus the valuation of B. Okay, so you think valuation is like tropical setting ring, it turns multiplication into addition. And then the valuation of A plus B is at least the minimum of the valuation of A and the valuation of B. Okay. And if you've never played with valuations before, the first exercise is to check that if the A and B have different valuations, then this is actually equality. Okay, so you can think about it for most whose pairs A and B, valuations are behaved like the tropical setting ring. Multiplication is addition, and addition is almost minimum. Okay, what are some examples? So the first is your favorite field is a field with a valuation. Just whatever your favorite field is, it's just the valuation might be trivial. So I could take, for example, the complex numbers and take the valuation that says the valuation of everything is 0. So I might take K to be the complex numbers, and the valuation of A is 0 for all A is equal to 0. Okay, so clearly this satisfies my two axioms. 0 equals 0 plus 0, and 0 is at least the sum of 0 and 0. Okay? And if you're worried about what happens when A plus B is 0, well, we say the valuation should be infinity then, if we want it. Okay, we might take K to be the Cazaux series. Okay, so this is, I can take the union for n greater than or equal to 1 of Laurent series in 1 over n. Okay, so that means elements here are Laurent series with fractional exponents, and we have a bound of the exponents. So the valuation of something like, I might have 3 times t to the minus a half plus 7t to the 5/3 plus 8t to the 11th plus dot dot dot. Okay, so I have some Laurent series here, and the valuation will be minus a half. Okay, so all I'm doing is I'm keeping track of this lowest exponent that shows up. Okay, so you can check, if I, first of all the Cazaux series form a field, they are algebraically closed, and this is a valuation. So if I take the lowest exponent of a product is the sum of lowest exponents. The lowest exponent of a sum will be the smallest exponent that showed up, unless maybe the lowest exponents cancel, in which case it will only get larger. Okay, so this is a perfectly good valuation. And then the third one you might be familiar with is I might take K to be dq, and I'll take the p-adic valuation. So this is going to be the valuation of e to the n times a over b is n if p does not divide a over b. So the 2-adic valuation of 8 is 3. And the 3-adic valuation of 5/6 is -1. Okay. So here we have 3 different choices of valuations. Okay. I will mostly want an algebraically closed field, but you can always pass to Q bar here and then take the extension of the valuation. Okay, so this is it's a good one to do examples, and maybe if you'd rather have an arithmetic connections instead of algebraic connections. Okay, so what do we want to do with valuations? So what I want to do is I want to start with a polynomial and tropicalize it. So that means a polynomial over a usual field. And what we're going to do is, if you give me a normal polynomial, I'm going to read every plus sign as a tropical plus. I will read every multiplication sign as tropical multiplication. And I have to do something with the coefficients, so I'm going to take their valuation. Okay, so given a Laurent polynomial, in K, okay, its tropicalization is going to be in it's going to be trop F from Rn to R. I think about a polynomial like this as a function from k star to the n to k. So given by trop F of W is the minimum of the valuation of Cu. So I should write my function F is going to be the sum Cu x to the u. So here I'm using multi-index notation. So this means x1 to the u1 times x2 to the u2 up to xn to the un. So my u here live in z to the n. So it's going to be the minimum of the valuation of Cu plus w dot u. Okay, so let's pause and think about this. What I've done here is I've turned this addition into tropical addition. I've turned the multiplication here into tropical multiplication, okay? See, and I've taken the valuation of the coefficient. So I've got a valuation of a coefficient. There's the Cu times x to the u. Now I said x to the u is x1 to the u1 times x2 to the u2, and so on. That means u1 times x1, u2 times x2, plus u3 times x3. So that's my dot product here. Okay, so this is just, we had addition, turns into tropical addition.
Yeah, maybe this is so there for you. Maybe you can define a round polynomial.
Okay, yeah. So multiplication into addition and coefficients to their valuation. So the question was Laurent polynomial. So this means we're allowed, it's a polynomial in x and x inverse. So maybe if it's easier if I write down an example. So let's write down if k is, well, let's do the first, k is q, and I take the 2-adic valuation. So first let's take x inverse plus 4x squared y inverse plus 3y squared. Okay, so this is an example of a Laurent polynomial. It's a polynomial in both x and x inverse y and y inverse. if I tropicalize it, trop f applied to W is going to be, it's the minimum of the coefficient here is 1, which has valuation 0. So I get 0 plus minus W1, U2 plus 2W1 minus W2, and 0 plus 2W2. Okay, so this is taking the multiplication again to addition, addition to minimum, and taking the valuation of the coefficients. So this, here's my some color, this 2 comes from this 4. Okay, the two-adic valuation of 4 is 2. The valuation of all the other coefficients is 0, so this 3 turns into a 0. The 1 that I didn't even bother writing turned into a 0. This 2 and a minus 1 are that 2 and that minus 1. This minus sign is that minus sign, and this 2 is this 2. And do one more example, and then we'll check the questions. Okay, if I let me take a quadratic polynomial this time. So f is 6x squared plus 5xy plus 10y squared plus 3x minus y plus 4. Okay, so trop f is, okay, I have to take addition, remember, to minimum multiplication to addition and the valuation of the coefficient. So again, I'm going to take the two-adic valuation. So I'll get, let me just write it as a polynomial in x and y. It's going to be the minimum of 2x plus 1, x plus y, 2y plus 1, x, y, and 2. Okay, so the 4 turned into a 2, minus y turns into y, 3x turns into x, 10y squared turns into 2y plus 1. Okay, the 10 turns into the 1, the y squared turns into the 2y. And if we draw a picture of that, the domain looks like this. So I have here, this is 2, the function y, 2y plus 1, x, 2x plus 1, and x plus 1. Okay, so this is an example, so we know the tropical hypersurface determined by this tropical polynomial will be this union of line segments you see in this case. So this is a tropical, we had quadratic curves this morning, here's a tropical quadratic curve. Okay, so maybe questions about tropicalization? Rule again, we just do 3 things. Everything you see, every operation you regard as a tropical operation, where if you see a field, you turn it into its valuation. Okay. So we want to now tropicalize hypersurfaces. So that just means I'm going to take the polynomial, my classical polynomial, I will tropicalize the polynomial, and then I'll take the tropical hypersurface. So given, again, f in my original polynomial, the tropicalization of the hypersurface I'll use just the notation v of f for the variety defined by the polynomial f. So is the tropical hypersurface defined by trop f. Okay, so again, so it equals the set of W in Rn, where the minimum is achieved at least twice. So maybe we can already see a little bit for the quadratic equation. If I have a quadratic equation over a field with evaluation, and I look at I tropicalize it, any root is going to have to, well, when I add up all the terms, I have to get to 0. So in particular, the smallest valuation terms have to cancel. Okay, so the minimum must be achieved twice. So that's sort of saying why I know that the roots, their valuations have to be in my tropical, have to be roots of the tropical polynomial. Okay. And maybe, okay, got it. So maybe I can say a little bit, maybe why did I say Laurent polynomial as well? Also, the one thing you should notice is what happens if I multiply my polynomial by a monomial. Let's say note that if I take the tropicalization of x to the u times f, remember x to the u is my shorthand multi-index notation, so this could be x squared times y cubed. Well, remember multiplication turns into addition, so this is the tropicalization of x to the u plus the tropicalization of f. So as a function, x to the u times f applied to some vector w, that's going to be the tropicalization of x to the u. It's just going to be w dot u plus trop f of w. Okay? So so remember we're looking at the non-differentiability locus or the non-linear locus. What you'll notice is that this function is going to be differentiable or linear exactly where this function is. Okay, so the tropicalization of the variety of x to the u times f equals the tropicalization of the variety of f. Okay, because remember our definition here is tropicalize the polynomial, take the tropical surface. Okay, yeah?
So the question about the definition of the tropical hypersurface. If you have a monomial, how do you define it?
If I just have a monomial, so there it's going to be, so there, I guess it should be empty. So it's the empty set, yeah. Because it's going to be the non-linear locus. Okay, and why does that make sense? Okay, what's the point of what we're saying here? Let's think geometrically now. What are we saying if we say that the variety doesn't change if you multiply by a monomial? I'm saying that I don't care what's happening. If I want to, I started talking as if I was talking about affine varieties, but I'm saying I don't care about what's happening on the coordinate hyperplanes. So that's why I had a Laurent polynomial ring, because the Laurent polynomial ring, you should think of as the coordinate ring of the algebraic torus. Okay, so this explains, means, so i.e. we only consider varieties in case for R to be. Okay, the Laurent polynomial ring is the coordinate ring of the algebraic torus, and what we're seeing is it doesn't make any difference if you change each polynomials. Okay, so that's tropicalizing hypersurfaces. What we want to do now, though, is, if you like, the very first half of the lecture, we were going through school mathematics. We did the quadratic, how to add, subtract, multiply. We did the quadratic formula. We're now coming up to starting our first course in algebraic geometry. Okay, so what's a tropical variety? If I start with so I've said already I want to start not just with affine varieties, but with subvarieties of an algebraic torus. So if I start with a subvariety of the torus, and I want to tropicalize it, well, what should I do? Classically, a affine variety is just the intersection of a bunch of hypersurfaces. So we want to mimic that in the tropical world. Okay, so I'm going to write y to be the variety of an ideal I, being k star to the n, where I is an ideal in my unwanted volume. So now trop f, do the tropicalization of y. Trop y, it's going to be the intersection over all f in the ideal of trop of v of f. Okay? So if I have a variety, it's the intersection of some hypersurfaces, I just intersect those. What we're saying here is that my tropical variety is the intersection of some tropical hypersurfaces. So there's one obvious sort of slightly, well, you might wonder why I've written it this way, and I'm going to come back to it at this point in a moment, but let's do some examples before we come back to this point. Okay, you might think, well, normally affine varieties, polynomial ring is Noetherian, I would cut it out by finitely many objects. Sorry, where? That's how I find it. Okay. Yeah, so the definition of this was take the polynomial, tropicalize it, take its tropical hypersurface. But this was the notation I chose. Okay. Let's do some examples. If I take y to be what looks to be something very boring, we'll take x plus y plus z plus w and x plus 2y plus 5z plus 11w in c star to the fourth. Okay, so you look at this, and this is just c with the usual trivial valuation, so forget about valuations for a moment. What is this? I mean, if I was working as an affine variety, it would be incredibly boring, right? This would be linear algebra. It would just be a two-dimensional subspace of c to the fourth. Because I'm working in the torus, it turns out life's a little easier, a little more interesting, because what I remove turns out to tell us a lot of information. But let's do it first. So the first fact is if x is in trop y, so then it turns out that we have the following nice property. This is maybe at the moment this is an exercise. We can say x plus lambda times 1, 1, 1, 1 is in trop y. Okay, so this is going to be true, and it will be clearer, maybe by tomorrow, why this is true whenever we start with homogeneous polynomials. So if I have this property, then I can just add the all ones vector, any multiple, and stay in my tropical variety. Okay? This means that I may as well draw pictures in r to the fourth. This lives in r to the fourth, but I may as well draw the picture in r to the fourth mod the all ones vector. So we'll draw trop y in r to the fourth mod the all ones vector. So that looks like r to the 3, r cubed. And in that case, it's going to be just, I take the positive vectors, and this is the all negative 1, negative 1, negative 1. So 1, 0, 0, 0, 1, 0, 0, 0, 1, and then this negative, sorry, this is not a great picture. You have to imagine the positive orthid, and then the negative, negative, negative. This is really coming from, I've chosen here this identification where I make the last coordinate 0. So this is really the 4 coordinate directions modded out. Okay. Why is this? Well, you have to first think, what are these tropical hypersurfaces? Okay. If I just tropicalize one hypersurface, I want the minimum of x, y, z, and w, and I need that minimum to be achieved at least twice. So that's going to be all numbers, all vectors where the smallest coordinate appears in two positions. Those of you who are familiar with toric varieties, I like to think of this as the fan for projective space with the top dimensional cones taken away. Then I now have to, this is why you'll notice, this is why I stated my definition in a slightly funny way. Because that's also the same as true here. Okay, as tropical polynomials, these are the same, right? Both of these tropicalize to the minimum of x, y, z, and w. Okay, so when I intersect their tropical hypersurfaces, I get the same thing. Okay. However, if I rewrite them, I can take linear combinations even of these two polynomials and get something with a different tropicalization. For example, if I took y plus 4z plus 10w, if I did my arithmetic correctly, that's now, we're looking at the minimum of y, z, and w. So its tropical variety will be different, and I have to intersect all ways a priori to take linear combinations. So maybe, let me just say something about that. So in the warning, so if y is the variety cut out by f1 up to fr, so if I have a bunch of polynomials and y is just the common zero locus of my polynomials f1, f2 up to fr, then we don't necessarily have, then trop y is not, at least in general, equal to the intersection from I equals 1 to r of trop of v of f. Okay. So normally you take the classical polynomials, you tropicalize. So normally for classical variety, I give you the generators of the ideal, and you say I just need the points where these polynomials will vanish. This is not true tropically, and this is an example. These, if you intersect these, you get something that's at one bigger dimension than what we got here. Okay? But it is true, though, that they always exist. So generating sets, for I with trop, where we have with equality are called tropical bases. And this might be more than a minimal generating set. So if you know, if you're familiar with Grosvenor bases, this will be a phenomenon you've seen before. So let me do one more example of this tropicalization procedure, and that will be if I start with so this will be a tropical elliptic curve. So I'll start with a cubic polynomial in my two variables, and here it's easier to work over the Poisson series. So let's do. So f is t cubed x cubed plus x squared y plus xy squared plus t cubed y cubed plus x squared plus t inverse xy plus y squared plus x plus y plus t cubed. And this is a polynomial in, well, a Laurent polynomial in x and y with coefficients as Poisson series. Okay, so the first thing we do is we tropicalize this. So trop f is going to be the minimum of what, 3x plus 3, x, 2x plus y, x 2y, 3y plus 3, 2x, x plus y minus 1, 2y, I've got my x, y, and 3. Okay, so as a function, so this is a function again from R2 to R2. What does it look like? So here's my picture of my tropical elliptic curve. So I have 3 directions going to the left, 3 going up, 3 going in this -1, -1, -1 direction. Okay, it turns out no matter what tropical degree 3 polynomial you take, we're going to have that up to some issues with, we'll talk later in the week about multiplicity, but up to multiplicities, we'll always, if I start with something of degree 3, I'll always have 3 things going to the left, right, 3 things going upwards, and 3 things going down. And then you can see we've got a cycle, so in the same sense, you think of an elliptic curve, something with genus 1. Here is my genus 1. And being seen in my tropical curve. So somehow, this illustrates a lot of what we want to understand, use tropical geometry for. We're starting with a variety, we want to get some idea, handle on it, but we tropicalize and turn it into something simple, hopefully simple. So in this case, for example, the length of the cycle is the tropicalization of the J invariant of the elliptic curve. So we can read off some information, sorry, it's the valuation of the J invariant. So we can read off some information about the elliptic curve from this picture. Okay.
For a principal ideal, you get the tropical basis.
For a principal ideal, we just take, the generator is the tropical basis. Yeah, so that actually, in some sense, that's an exercise to say the 2 definitions I gave of tropical variety were the same, right? Because when a priori, you might have to take all multiples of f. But if you do that, you don't get anything. Yeah.
And you said the length of the cycle is 6.
So in this case, we'd have to, in this case, so what we normally mean is the lattice length. So that means these are going to be, we'll see that these are always rational directions. So there's a notion of a lattice length, which more or less means I count the number of lattice points. And so it's the length in that sense. And maybe more questions?
You said how to get a tropical basis, but I didn't hear it.
No, actually, no, so I didn't say how to get a tropical basis. That's because that's a hard question. Okay, so they always exist. So maybe I should say that these exist. Okay, but at the moment, this is sort of tropical geometry is a young field. At the moment, we have I can give you 2 answers which are both bad in their own right. One is, in some sense, tropical varieties are always complete intersections, in the sense that I can always find a tropical basis of size the codimension. However, this is not a good answer because the polynomials we need, that's without the generating set. So if I don't worry about it generating I, just cutting out the intersection being set theoretically correct, the polynomials might be an enormously high degree, so this is impractical. It doesn't necessarily tell you anything geometric. The other thing is, if you give me degree bounds for the polynomials, I can give you degree bounds for a tropical basis, but that's also not so useful in practice. So, and somehow this is something. So maybe I should say, why do we? So I guess I'll finish by giving the philosophy. The philosophy is going to be, we want to recover properties of the variety from the tropical variety. So the philosophy, or the guiding question, is which properties of Y, or of compactifications of Y, covered from tropically. And maybe, so just to give you some idea, one thing we will see tomorrow is that the dimension is one such fact. Okay, every picture I've drawn here has been, well, the clear pictures have been pictures of curves, and my tropical variety was one-dimensional. I had my picture of something that looked like it was a two-dimensional subspace of the torus, and I drew a one-dimensional thing, but I told you I'd already quotiented out by one dimension. So I had something two-dimensional. So dimension is going to be preserved, but many more sophisticated things. Actually, I mean, everything I think we'll hear about probably from Joe this week has most of a tropical counterpart. There's a theory that's been developed over the last few years of tropical intersection theory. So basically it's in nice cases we can understand the intersection theory of my variety or of a good choice of a compactification. So you might not think at the moment that you care about subvarieties of a torus. By the end of the week, I want to convince you that you do, because you can care about compactifications of subvarieties of tori. Let's do the simplest example, just to finish with this, is, so recall, so let's say, I'll just make an observation that any projective variety, I'll write it as y bar, is a compactification of some y in case phi. Okay, you start with your projective variety, embed it into some projective space, take the intersection with the torus. So assume you've chosen a non-degenerate embedding, so it intersects the torus of projective space. That's all the points where all coordinates are non-zero. That's going to give me a subvariety of a torus. And the idea is that if you've chosen coordinates well, the tropical variety there is going to tell you something about your original variety. Okay, so this is our guiding question, and we'll hopefully during the rest of the week see some more ideas about see what answers we understand so far. But it's a new field, and maybe you'll solve some of the questions. So maybe let's stop there for questions.